Hello guys, welcome to my YouTube video. Before I start my video, don't forget to like and subscribe. Share. Hi, Assalamualaikum. My name is Muhammad Danil Zikry bin Ezani and my matric ID is MH20066. I'm from University Malaysia Pahang, student of Bachelor Degree Mechanical Engineering Automotive. This is my assignment for BMA 2312, Introduction to Automotive Engineering, conducted by Dr. Rizaman Mamat. Today, I'm going to present about the STIRLING engine. So, what is STIRLING engine? A STIRLING engine is a heat engine that is operated by the cyclic compression and expansion of air or other gas, like we can say the working fluid, at different temperature, resulting in a net conversion of heat energy to mechanical work. More specifically, the STIRLING engine is a closed-cycle regenerative heat engine with a permanent gaseous working fluid. Now, let's talk about history of this STIRLING engine. Who invented it? His name is Robert Stirling. Robert Stirling is considered one of the father of hot air engines, notwithstanding some early predecessors. He is notably Guillaume Amatons, correct me if I'm wrong, that is the person who succeeded in building. In 1699, the first working hot air engine are invented. He invented the air engine because steam engine would explode and harm workers. To make you understand about Robert Stirling, now I will show you the video of the history of this STIRLING engine that made by Robert Stirling.
This trend is also generating new interest in an invention that dates back 190 years, the STIRLING engine, named after its inventor, Reverend Robert Stirling. Robert Stirling was born on the 25th of October 1790 near the Perthshire village of Methven in Scotland. His contact with engineering started at an early age. In 1756, his grandfather Michael had developed the first rotary threshing machine for agriculture. Helping his father maintain and service the machines, young Robert showed a keen interest in anything mechanical. From 1805 to 1808, he attended Edinburgh University, where he studied Latin, Greek, logic, and mathematics. A year later, he switched to Glasgow University to study divinity and law. Graduating on the 4th of July 1815, he was ordained a minister of the Church of Scotland, a vocation which he followed till his death in 1878. In the first half of the 19th century, Europe underwent a technological, economic, and social transformation. In the early days of the Industrial Revolution, working conditions were appalling. And Stirling witnessed them at first hand in his parish. In the coal mines, new high-pressure steam engines were introduced to drive pumps for extracting the mine water. The human cost was high. The boilers frequently exploded and claimed many lives. Among the victims, children as young as 6, forced to work in the mines. Driven by the idea of making the miners' work safer and easier, Robert Stirling sought to develop a machine that would operate at much lower pressure and without dangerous steam. Although the principles of thermodynamics were not yet known, Stirling was aware that gases expand with heat and contract with cold. This can be demonstrated by a simple experiment. If a paper lid is placed over a jar of hot jam, the air inside the jar is heated. This causes it to expand in the jar and force the lid to belly outwards. But if the jar is placed in cold water, the air inside cools down and contracts, and the lid curves inwards. Stirling was inspired to design a machine that exploits this property of gases. The principle on which it works has been known since antiquity. In the 2nd century BC, the scholar Hero of Alexandria developed a machine for opening temple doors automatically. When a visitor lit a votive fire, the heat spread to a sealed underground tank half filled with water and caused the air inside it to expand. The resulting pressure forced the water through a pipe into a bucket. Because of the weight of the water, the bucket descended, pulling a rope that opened the doors. When the fire went out, the air quickly cooled and contracted. A partial vacuum was created. The water in the bucket was sucked back into the tank, and a counterweight closed the doors. Like Hero's hot air machine, Robert Stirling's invention exploited the property of air to expand with heat and contract with cold. On the 27th of September 1816, he obtained a patent in Scotland for a hot air machine that was later to become known as the Stirling engine. This is how it works. A sealed cylinder is exposed to a continuous source of heat from below. The air in the lower part of the engine gets hot, expands, and pushes a piston upwards. Now the hot air needs to be cooled again. This is done by adding air fins to the farthest point from the flame and getting the air to flow towards them. So the air at the bottom needs to be displaced, a task that's performed by another piston, which displaces the air as it descends and forces it up to the air fins. There, the air cools and contracts, and the power piston returns to its starting point. Now, when the displacer piston makes space for the air at the bottom, the air is reheated and the cycle starts again. To ensure coordinated movement, the power piston and the displacer piston need to be precisely synchronized. This is achieved by coupling the two pistons with a flywheel. The piston rods are anchored in such a way that the pistons move in perfect coordination through each stage of the operation. While the power piston travels upwards due to the expanding hot air, the displacer piston remains virtually motionless. Then the displacement of air to the cold end of the cylinder begins. Finally, the two pistons return to their starting points. The cooled air is displaced downwards to be heated, and the cycle starts all over again. Robert Stirling's hot air engine was a safe alternative to the steam engine because the internal pressures involved were much lower. Coal was needed only to provide the required heat. But apart from being a great deal safer than the steam engine, Stirling's invention was more fuel efficient, reason enough to develop the new technology further. The first Stirling engine was used in Ayrshire, in Scotland, to pump water from a quarry. By 1840, Robert and his brother James, an engineer and foundry manager, had developed and patented a number of improvements to the Stirling engine. In March 1843, a 34 kilowatt unit was built to drive all the machinery at the Dundee Foundry Company. For 4 years in operation, it consumed only a third as much fuel as the steam engine it replaced. Its efficiency ratio, 18%, was never matched in the 19th century. The steam engine in those days managed less than 10%. Robert Stirling was not an industrialist, so he spent no more time developing and marketing his idea. He attended instead to his duties as a clergyman. Robert Stirling remained a Presbyterian minister for the rest of his life. He died on the 6th of June 1878 at Galston in Ayrshire. He was nearly 88. But his idea, the Stirling engine, lived on. At the dawn of the 20th century, around 250,000 Stirling engines were in use worldwide, as fans, pumps or drive units for small pieces of equipment. They supplied private households and small businesses with mechanical power. Their advantage was that they needed only heat to work, so any combustible material could be used. But as internal combustion engines and electric motors became more efficient and widespread, Stirling engines gradually disappeared from the market. Then, in 1937, a number of companies started looking at the Stirling engine as an option for generating electricity in remote areas. Today, there are various types of Stirling engine. One of the most widespread is the Alpha type. Here, the engine is comprised of 2 separate cylinders and 2 power pistons, one hot and one cold, connected by a pipe. The left cylinder head is exposed to a heat source. The one on the right is cooled by air fins. In the first phase, the left cylinder is heated and the expanding air pushes the left piston down. Then the right piston moves down. The hot air is sucked into the cold cylinder and cooled. This creates a partial vacuum in the power cylinder, which pulls the power piston back to its original position. At which point, the cycle starts all over again. Owing to the alternating transfer of air between hot and cold cylinders, continuous motion is achieved in the engine. Today, there are many applications for the Stirling engine. Its simple principle and design makes it an attractive low-maintenance option. And with air pollution and emissions such a major issue, the closed-cycle engine is experiencing a renaissance. Because it can run on any kind of fuel, renewables in particular. Even biogas or sewage gas from treatment plants could be used as an alternative to petrol, diesel, or the fuel originally used, coal. But the fuel doesn't even need to be combustible. Geothermal or solar energy can also be harnessed to power a Stirling engine. If the heat source is non-combustible, as in the case of solar, the system is totally emission-free. In terms of versatility, the Stirling engine is in a class of its own. In arid areas, for example, lots of mechanical power is needed to pump water and lots of sunlight is available. Here, dish Stirling systems are a particularly suitable technology. Fitted with a parabolic dish to focus the heat of the sun's rays, they use a Stirling engine to power a generator for the production of electricity. Thanks to this capacity to generate electricity from renewable resources, the Stirling engine faces a bright future as a machine for a clean world. Even very small differences in temperature, like that between the heat of a human hand and the temperature of the air around it, are enough to set a Stirling engine in motion. And as long as that temperature difference is present, it keeps on running. In contrast to internal combustion engines, with all the noises generated by explosions and ignitions, Stirling engines run very quietly indeed. This is because there are no pressure peaks in the operating cycle, a fact that also makes for virtually vibration-free operation and considerably extends the life of the engine. But the big argument in favour of the Stirling engine is resource conservation, which makes up for drawbacks such as slowness and low power-to-weight and mass ratios. So the time seems ripe for a renaissance of the Stirling engine. Even today, as in Robert Stirling's time, it could help make a considerable difference to the world.
Okay, now let's talk about how this Stirling engine works. This Stirling engine works by heating and cooling a gas inside a sealed chamber. Just like we put a fire or ice cube in the sealed chamber. If the gas heating, so it will be facing expansion. And if the gas cooling, so it will be facing contraction. Okay, this Stirling engine works by using the Stirling cycle principle. The Stirling cycle principle is made by Robert Stirling. The key principle of a Stirling engine is that a fixed amount of gas is sealed inside the engine. Stirling engines are external combustion engines, since the heat is supplied to the air inside the engine from a source outside the cylinder instead of being supplied by fuel burning inside the cylinder. The diagram above is the illustration of this principle. Now, what are the parts of the Stirling engine? The Stirling engine parts are furnace, generator and Stirling engine itself, cooler, regenerator, hot heat exchanger, air preheater, air input, economizer and heat consumer. Above this is the illustration of Stirling engine parts. So now let's reload to the video that I will present next to understand how this Stirling engine works.
In this video, I'm going to talk a little bit about how a simple Stirling engine works. The Stirling engine is a fascinating device that converts a temperature difference directly into mechanical work. This is a simple one that runs using just a small temperature difference. Hot water near the hot side and room temperature on the cold side are enough to make it work. So if I put it on top of this cup of hot water, it'll be able to run in just a minute or two. While we wait for it to heat up, let's see more about how a Stirling engine works. Let's start with an airtight cylinder. Sometimes this is filled with a gas such as hydrogen to maximize efficiency, but ours will just be filled with air. When the cylinder is heated, the air pressure inside will go up. When the cylinder is cooled, the air pressure inside will go down. Now we'll add a small cylinder at the top with a piston. If it weren't for the piston, this would be a hole in the top, but the piston makes it airtight again. The piston slides up and down as freely as possible while keeping the cylinder as airtight as possible. If we heat the cylinder, the air pressure will increase compared to the outside air pressure pushing the piston up. If we cool the cylinder, the air pressure will decrease compared to the outside air pressure pushing the piston down. Let's add a displacer. The displacer moves the air to the top of the cylinder or to the bottom of the cylinder. Notice the gap between the outer edge of the displacer and the edge of the cylinder. The gap is big enough to allow air to freely flow around the displacer, but small enough that most of the air is displaced to the top or bottom. Now if we heat one end of the cylinder and cool the other end, we can use the displacer to quickly heat or cool the air inside and move the piston up or down. With the displacer at the top, the air moves to the bottom and heats up. With the displacer at the bottom, the air moves to the top and cools down. Now let's link the piston and the displacer in such a way that the piston and the displacer drive each other. Notice that the displacer is at the top of the cylinder when the piston is at the halfway point. The air is at the bottom of the cylinder, so it will expand and push the piston up. As the piston reaches the top, the flywheel momentum moves the piston back to the halfway point. Now the displacer is at the bottom and the air is on the cool side at the top of the cylinder, so the piston will be pulled down. As the piston reaches the bottom, the flywheel momentum again moves the piston to the halfway point and the cycle begins again. Okay, let's give it a try. We have to give it a boost because part of the cycle requires momentum. Notice that it's running counterclockwise. One interesting thing is that if we reverse the hot and the cold sides, it can run in reverse. But you may have also noticed that Stirling engines don't start right away. There has to be a sufficient temperature difference between the hot and the cold sides before it'll run. So in this case, the bottom has to get cooled down a little bit. Stirling engines are not widely used, but they do have some appealing characteristics. They're quiet, they're efficient, and they can take advantage of any heat source, including renewable sources such as the sun. At its core, the Stirling engine simply takes advantage of the expansion and contraction of gases as they are heated and cooled. Thanks for watching and have a good day.
Okay, next, these Stirling engines are built after steam engines are made. So, this is the difference between Stirling engine and steam engine. As you can see at the table, for Stirling engine, it is very clean and economical engine. This engine is a very curious mechanism because this engine need only the temperature variation. For steam engine, it is easy to explode and has a high of waste temperature steam. This next video will explain why steam engine need to change to Stirling engine.
Engines have been empowering our world since the Industrial Revolution. First, dirty coal-powered steam engines, and then cleaner and more efficient gasoline engines, and recently jet engines in airplanes. The basic concept of an engine is something that exploits the difference between high temperature and low one. One engine you may have heard a lot about is Stirling engine. And in this video we are going to learn about Stirling engine. Please watch our video till the end. Subscribe to our channel and press the bell icon. So let's begin to our today's topic. Engines that drive vehicle or factory machines are examples of what scientists call heat engines. They burn an energy-rich fuel, that is coal, gasoline, petrol, or diesel, to release heat energy, which is used to make a gas expand and cool, push a piston, turn a wheel and drive the machine. Both types of engines, that is internal combustion and external combustion, works on the same principle. That is the science of thermodynamics, literally how heat moves. Before we can discover what's so good about Stirling engines, it helps if we know what's so bad about steam engines. In a steam engine, coal fire heats up water and make it boil and them turn into steam. The steam travels down a pipe to a cylinder, through an open entry valve, where it pushes a piston and drives a wheel. The entry valve then closes and exit valve opens. The momentum of the wheel makes the piston return into the cylinder, where it pushes cooled unwanted steam out through the exit. There are many problems with steam engines, but here are 4 of the more obvious. First, the boiler that makes the steam operates at high pressure and there is a risk that it could explode. Second, the boiler is generally some distance from the cylinder, so energy is lost getting the heat from one to the other. Third, the steam leaving the smokestack is still quite hot, so it contains wasted energy. Fourth, because the steam is ejected from the cylinder each time the piston pushes, the engine has to consume huge amounts of water as well as fuel. So can we design an engine that overcomes these problems? Suppose we get rid of the boiler, which would solve the risk of explosions, and use the heat from the fire to power the engine directly. Then, instead of using steam to move heat energy from the fire to the cylinder, why not put the cylinder nearer to the fire and use ordinary air or any other form of simple gas to move the heat energy between them? If we seal this air in a closed pipe, so the same air moves back and forth over and over again, picking up energy from the fire and releasing it in the cylinder, we solve the problem of the engine needing a constant supply of water. Finally, why not add some sort of heat exchanger so that as the hot air passes back and forth, its energy is retained inside the machine and recycled to improve the overall efficiency. These are the essential ways in which a Stirling engine improves on a steam engine. You'll sometimes see Stirling engines described as closed-cycle, regenerative heat engines, which is a very terse way of saying what we just said. Closed cycle means they use a sealed volume of gas to move heat back and forth, over and over again, through a series of endlessly repeated steps. Regenerative simply means that they use heat exchangers to retain some of the heat that would otherwise be lost on each cycle. Like a steam engine or an internal combustion car engine, a Stirling engine converts heat energy to mechanical energy, work, by repeating a series of basic operations, known as its cycle. It operates by cyclic compression and expansion of fluids at different temperatures, such that there is a net conversion of heat energy into the mechanical work. More specifically, a Stirling engine is closed-cycle regenerative heat engines with a permanently gaseous working fluid. So guys, that was about Stirling engine. If you like this video, please hit like. If you have questions, you can comment below. Thanks for watching this video. Happy learning!
Okay. Four advantages. First, the silence of operation. Combustion is continuous outside the cylinder. In addition, its design is such as the engine is easy to balance and generates a few vibrations. Second, the high efficiency. It is function of the temperature of the hot and cold sources. Third, the multitude of possible hot sources. Combustion of various gases, wood, sawdust, waste, solar, or geothermic energy. Fourth, the ecological aptitude. To respond to the environmental requirements on air pollution, it is easier to achieve a complete combustion in this type of engine. Fifth, reliability and easy maintenance. The technological simplicity makes it possible to have engines with a very great reliability and requiring little maintenance. And lastly, the very diverse uses. It is because of its autonomy and adaptability to the needs and different kinds of hot sauce. For disadvantage of Stirling engine, first, the price. The price is cost is probably the most important problem. It is not yet competitive with other means of power. Second, the ignorance of this type of engine. The ignorance of this type of engine by the general public. Only a few fans know it exists. It is therefore necessary to promote it. Third, the variety of model. The variety of models prevents standardization and consequently lower prices. Fourth, the problem of ceiling. The problem of ceiling are difficult to solve as soon as one wishes to have high pressure of operation. The choice of ideal gas would be hydrogen for its lightness and its capability to absorb the calories, but its ability to diffuse through material is a great disadvantage. Fifth, heat transfers. With a gas. For the last topic in my presentation, I will talk about why Stirling engine not commonly used. The Stirling engine not commonly used is because the gases used inside the Stirling engine never leave the engine. It will make the Stirling engine hot, and there are no exhaust valve that vent high pressure gases as in gasoline or diesel engine, and there are no explosion taking place. Because of this, Stirling engine are very quiet. The Stirling cycle uses an external heat source, which could be anything from gasoline to solar energy, to the heat produced by decaying plants. No combustion takes place inside the cylinder of the engine. Okay, we reached to the final of my presentation. Thank you for listening through my video presentation. My name is Muhammad Danil Zikry bin Ezani. Till we meet again in other video. Assalamualaikum and bye-bye.